Hey guys, so in the last lecture we have discussed kurtosis. So in today's lecture we are going to discuss reliability of a repairable system. So what is the reliability after any system on a product is repaired? So that we are interested in today. So reliability of a repairable system, that any product that that is repairable or not, that is also reliability. So if I bought any product and that product can be repaired or not, so that is also an important point. So first let's understand what is a repairable system. So what is a repairable system? So a system is a collection of two or more parts. So repairable system. So a system is a collection of two or more parts which is designed to perform one or more functions. A system can be either non-repairable or repairable. So either a system cannot be repaired, you have to buy a new, or it can be repaired. So a non-repairable system, for example, electric bulbs, thermometer, etc., in the event of a failure, cannot be brought back to working condition as it is discarded for the first time. So here example we are giving as a thermometer. So it cannot be repaired once suppose the glass is broken, or in the case of bulb, if the filament is broken, so it cannot be repaired because the cost of this equipments are too low, and the cost of repair can be as high than the cost of the new equipment. So it is not possible to repair. So in this condition it is discarded for the first time. It ceases it ceases to perform satisfactory. So a repairable system, like machines, industrial plants, software, etc., uh, it uh, it is a system which, after failing to perform one or more of its functions satisfactorily, can be restored to fully satisfactory performance by any method other than replacement of entire system. So a repairable system is that it can restore it can be restored to satisfactory performance to fully it can be restored to fully performance satisfactory performance. So that is called a repairable system. So repairable systems approach is rather different than non-repairable system by the fact that for the first type it is preferred counting the events rather than studying the times distribution. So a repairable system is a collection of items. If I want to define a repairable system, I can say that it is a collection of items which, after failing to perform, so it is a collection of items which, after failing to perform at least one of its required functions, can be restored to performing all of its required function by any method other than replacement of entire system. So it can be replaced. Uh, so so uh, it can be restored to performing all the required functions by any method other than replacement of entire system. So instead of replacing the whole system, it can be restored. Then the next is repairable systems are those which, an event of a failure, can be repaired. So for example, replacing a component. So you can replace a component rather than whole system, or repairing the component. That can also be the case. Either replace or repair the component. In some cases, the reliability of a system after repair returns the same state as before the failure. So it returns to the same state. So thus models for repairable systems must be able to describe the occurrence of the events in time and are inherently different from models for non-repairable system. So any system which is made repairable or non-repairable, their models are totally different. So once a system experiences a failure, different repair strategies have different influences on the system reliability, usually defined as a probability of no failure in time intervals. So a system for reliability, the system for reliability for a non-repairable system and repairable system, they have different strategies. So it is important to understand the type of system being designed and use the appropriate reliability methods and tools to match that system. So a non homogeneous poison process, non-homogeneous poisons process. So this poison is the poison's distributions poison, and renewal process and renewal process are the commonly used models for repairable system. So these are the commonly used models for repairable system. So the other point process models to describe repairable systems are modulated renewal process of inhomogeneous gamma process, that is IGP, is modulated renewal process of inhomogeneous gamma process and modulated gamma process, and other is power modulated power law process, and the last is exponential power law process. So these are the various processes to find the reliability of a repairable system. So now let's see what are the measurements of reliability. So what are the measurements of reliability? So what are the measurements of reliability? So basic measurement of reliability, let me write a measurement of reliability. So a basic measurement of reliability of a product, that is a probability, it is a probability of survival. So probability of survival is that of a mean time between failures. So that is mean time between failures, MTBF. Suppose n products are taken. Suppose n products are taken at a random. So n products are taken from a random from a large group, and nt of them are failed. So n products are being tested from a large group, and in this nt of them fail, end their life during the time period t. So during the time period t, they end their life. So then the probability, so let me write the suffix t. So the probability of failure during the period t is, that is pt, is equal to nt divided by n. So this is the probability of failure. So in order to evaluate the reliability, it is important to check the performance. So it is important to check the performance of the product over the intended length of time t. So the probability, pt will be equal to summation of I running from 0 to n, nt divided by n. So here, so the reliability rt, so reliability rt will be equal to 1 minus probability of failure. So 1 minus probability of failure, so that is 1 minus pt. So the reliability is equal to 1 minus probability of failure. So that is equal to 1 minus pt. So which is equal to 1 minus sigma I running from 0 to n, it is nt divided by n. So when a large number of products is tested, so that the reliability frequency nt upon n becomes a smooth function, that is f of t. So reliability rt will be equal to 1 minus 0 to t f of t dt. So in general, it is found that if the failure rate is approximately constant, then f of t assumes the form of the exponential probability density function. So f of t will be equal to 1 upon theta e raised to minus t divided by theta, where theta stands for MTBF. MTBF, that is mean life between failures. So now our reliability function for a specific period of time t will be equal to 1 minus 0 to t 1 upon uh, theta uh, e raised to minus t divided by theta into dt. If I take the integration of this, so I will get that is e raised to minus t divided by theta. So where t is the required life. So the failure rate lambda can be reciprocal of mean time to failure mttf, so that we can say that lambda is equal to 1 upon theta. So as we know that theta is mtbf, so from this reliability can be expressed as rt is equal to e raised to lambda t, because 1 upon lambda we are taking it as, so rt is equal to e raised to lambda t. So if the failure rate is not constant, there are other density functions like vbool, normal, gamma, which accommodate most of the pattern in practice. So these are the few uh, equations which we are using for reliability. Now let's see system reliability. System reliability. So a system or a complex product is an assembly of a number of parts or components. So a component may be in series or parallel, or it may be mixed system. So it can be a series, parallel, or a mixed system. So where the components are connected in series as well as parallel. So let's see for first that components connected in series. So first let's see series. So if the components of an assembly are connected in series, the failure of any one part the failure of any one part may be reason for failure of all the assembly. So it can fail all the assembly. In such cases, the reliability of assembly is given by the product of the reliability of individual components. That is, suppose a system consists of a four devices, that is P, Q, R, and S, and which can operate in series in in such a way that a failure in any one device can cause failure of the system. So assume that the probability that the P will operate, so P will operate with a failure for 100 hours is estimated to be zero point 0.9, and corresponding for Q is 0.85, and for R is zero point 0.8, and for S is 0.75. So these are the failure rates. uh, this is the probability. uh, so if the failure in PQRS are completely independent, and the probability that the system will operate without failure for 100 hours should be estimated, so the system failure will be into zero point 0.9 into 0.85 into zero point 0.8 into 0.75, so which will be equal to 0.459. So as you can see, the all the probability is greater than 75%, but the overall probability is reduced to 45% only of the system. So therefore, and if the system consists of n part, so the reliability will be equal to R1 R2 to multiplied by Rn. So in terms the failure rate, that is R will be equal to e raised to minus lambda it, where lambda I is the failure rate of the ith component. Now if the system is connected in parallel, so in that case uh, it is uh, in good condition. So when the components are connected in parallel system, so let qi is the probability of failure of the ith component, pi is the probability of a successful operation. So qi is the probability of failure of ith component, and pi, it is 1 minus qi, so it is a successful. So therefore the probability of failure of the system is given as, so probability of the failure of the system is given as q1 into so n into qn. So reliability of the system is nothing but r is equal to 1 minus f of t. So it is nothing but 1 minus p1 into 1 minus p2 and so on. So this is the system for connected in parallel. Now let's see the last system, that is mixed system. So third is mixed system. So for mixed system there are two devices, suppose X and Y, so which are connected in series. So these are having four components: 1, 2, 3 and 4. So the total there are four components for the system. Now the X and Y are connected in series, but the component 1 and 2 are connected in parallel. So in the same way, the device Y consists of two parts as 3 and 4 connected in parallel. The reliability of the device X will be equal to 1 minus P1 into 1 minus P2. For reliability for system Y will be 1 minus P3 into 1 minus P4. But the reliability of the system, total reliability, can be expressed as R is equal to Rx into Ry. So which will be equal to this multiplied by this. So that is nothing but 1 minus P1 into 1 minus P2 into 1 minus P3 into 1 minus P4. So this multiplication will be our answer for this mixed system. So I hope you understood this reliability. Let's see a small example. Uh, so an element has a probability of a successful operation over a given period of 60%. If four such elements are connected in parallel, find the improvement factor. So we have to find the reliability if there are four components. So we know that the reliability for parallel system is 1 minus f of t. It is 1 minus p1 into 1 minus p2 into 1 minus p3 into 1 minus p4. So it is 1 minus 0.6 into 1 minus 0.6 into 1 minus 0.6 into 1 minus 0.6. So it is nothing but 1 minus 0.4 into 0.4 into 0.4 into 0.4. So it is equal to 1 minus 0.4 raised to 4. So it is the value is 0.9744. So the that is 97%. Therefore the improvement factor is 0.9744 divided by 0.6, that is 1.624. So this is the improvement factor here. So this is an example which can be asked for 2 marks. So I hope you understood this topic today, that is system reliability. So thank you, and to see you in the next lecture. So thank you very much.